This is AP Calculus AB, and in this video, I'm going to finish the rest of the material in section 7.1. So if you remember last time, we did a lot of talk about slope fields, and we talked about separable differential equations and the basic methods for solving those. The thing we didn't get to talk about is what we call Euler's method. And so this is going to be pretty short because we're just going to go through how this method works. We're going to go through a couple of examples. So what I've got here are a couple examples, but I want to show you something else first. Okay, so what I have here is actually an animation from Geometer Sketchpad. And the idea here is to just give you a visual understanding of what's happening when we do Euler's method. So Euler's method is a way that I can approximate what the curve that represents the solution to a differential equation is going to look like. So we're talking about a particular solution to a differential equation. So if you look over here on this graph that I have on the screen, you can see that there's a slope field there, and there is what we call a starting point. So what we're going to do here is talk about, okay, how do I approximate this solution curve? Now, we talked about, kind of freehanding those, but there is a way that we can approximate the curve, and then we can get approximations for the solution to the differential equation at any point. And so this method of Euler's method, what it is just a bunch of linear approximations, and we're going to create a bunch of small line segments, and then we're going to connect them together, and they're going to start to resemble a curve. So the way this is done is actually very, very simple. We have a differential equation here. Y prime is equal to negative x over y. And we're going to start at this point. So this is just a random point. But what we would do at that point is we would calculate what the slope is at that point. And then we can figure out what the tangent line would look like at that point. Okay, so what we're going to do is essentially just draw in a line segment from that point. And in this case, I'm going to assume that I'm trying to approximate the curve to the right of this point. So I'm going to run through one iteration of Euler's method. And what I've done here is I've created a little line segment from that starting point. And that line segment is basically what the equation of the tangent line would look like on this interval, where we're saying essentially that this is the interval where x has a length of h units. So we went h units to the right, and then using the slope, we can figure out how far up we went. And then we get to a new ending point. And at that new endpoint, we just repeat the process. So then we get the slope again. We figure out if we move the same h units to the right, what's going to happen to the y value. And now we're at the end of the next segment. And then we just keep repeating that process over and over and over again. And eventually, as you can see here, you start to see all these line segments connected together start to resemble a somewhat smooth curve. So that's really what the process is that we're trying to do. So I wanted to show you that first so that you could have a good understanding of what was happening, because we're primarily going to do this in the form of a table, and you're not always going to have a good visual representation of what's going on. So I want you to try to keep that in your mind. This is the process that we're trying to follow. We're trying to piece together a bunch of line segments to create a curve. Okay, so getting back to the problem that we were originally looking at here, we've got a couple of problems for you to try. And there is a lot of stuff in this packet. I will warn you about using a TI-89 calculator, because that is what I would normally do in class. Obviously, I'm not expecting you to have your own TI-89 calculator. So if you can get yourself a TI-89 emulator and you want to investigate this, you can. But I'm going to go through it with you in class anyway. So really what I need you to understand is how to do this. Just really using a simple computational method that we're going to do by hand. What we're trying to do is get a feel for how this process works, because this is actually something we would never do by hand. This is something that would be an automated process, like using a TI-89 or using math software, or we could write a little computer program to do this. So it's actually really simple. Now, the idea here is to solve something like this first one. We're given this differential equation, dy dx is x plus y. And it says, let y equals f of x be the particular solution to this given differential equation with the initial condition for negative 1. So if you think back to that graph we were just looking at on that Geometer Sketchpad image that we had, we started at a point, and then we drew a line segment from that point. That's what we're going to do. We're going to start at 4, negative 1. And this says to use Euler's method starting at x is equal to 4 with 2 steps of equal size to approximate f of 4.2, and then show the work that leads to your answer. Okay, so what I'm going to do is kind of a streamlined approach here. And you'll see that I'm not actually going to find the equations of the lines. What I'm going to do is I'm going to have my point that I start at. I'm going to have my slope, which in this case is given by the equation x plus y. And then I'm going to have my delta x, which is the same thing as what we saw as h on that geometer sketchpad image a couple of minutes ago. And then my delta y is going to be determined by my slope and how far I move in the x direction. And that's going to get me to the end of the first line segment. X plus delta x, y plus delta y. Okay, so essentially this is just going to be a table, and I'm going to run through these calculations. So my first point I'm starting at is 4, -1. If I find the slope at that point, 4 plus -1 gives me 3. My change in x, well, notice it says we're starting at x is equal to 4 with 2 steps of equal size to approximate f of 4.2. Well, 2 steps of equal size, that's going to be a step size of 0.1 if I want to get from 4 to 4.2. Okay, so if I go 0.1 units in the x direction and have a slope of 3, I would have to go up 0.3. And now at the end of that line segment, I would be at x is 4.1. And from my y, I would just be at -0.7. Okay, so that's my first line segment in my Euler's method. So now for the second line segment, I'm going to start at that ending point, 4.1, -0.7. I'm going to find the slope, still x plus y. Okay, how far do I move in the x direction? That's always the same, 0.1 unit. How far do I move in the y direction? Well, I want to have a slope this time of 3.4. The easy way to calculate this is just multiply your delta x times your slope. Our change in y would be 0.34. And now at the end of that line segment, I'm at x is 4.2 and y is -0.36. Okay, so what I'm saying with that at the end then is I'm saying f of 4.2 is approximately -0.36. Now, that's not the actual solution. If we could solve this differential equation, which we could if we had some more advanced skills with differential equations, we could solve something like this and we could get the exact solution. But for us, we're using an approximation method. Now, we're pretty far off because we used actually a pretty large step size. And we did that because we're working this out by hand. The reality is, if we were going to do Euler's method to solve a differential equation, we would have a calculator like a TI-89 that would do it for us, or we could write, a really quick computer program to do it, or we'd have math software that had it built into it. So we can make our answer as accurate as we need it to be by changing that delta x or that step size. So the smaller the delta x is, the more accurate your end solution is going to be. Okay, so I've got another example here. This stuff in the middle is just how to do this on the TI-89. Again, you don't have to know how to do that. I'm going to show you this in class, but it's not something you have to know how to do. So what I want you to do down here is just another example similar to the first one, but I'm going to have you try it this time. So this time it says use Euler's method to find the approximate solution to the differential equation with this specified initial value. So we're going to use increments of size delta x, that's given here, and we're going to find y at 2.0. Now notice that we're starting at x is 0, and we want to get y evaluated when x is 2, and we're using a step size of 0.5. That means we're going to do 4 steps. So remember the setup here. We've got our xy, we've got our y prime, or I could write it as dy dx, and it's x plus y. I've got my delta x, I've got my delta y, and then at the end of that, I'm going to be at x plus delta x, y plus delta y. Okay, so those are my columns that I'm going to use. And remember, we're starting this time at the point 0, 2. And my step size I know is going to be 0.5. So what I want you to do is I want you to fill that out all the way until you get down to the point where you can approximate y at the value where x is 2.0. Okay, so you can pause the video. When you come back, I will show you the solution. Okay, so here's my worked out solution. And you can see there's not a lot to this. The main thing is you have to kind of understand what's actually happening when you look at this. So on the first line, I have a line segment going from 0.2 to 0.53. Next second line in this column, or the second row in this column, I'm at the point 0.53. I have a line segment that ends at 1, 4.75. Then I went from that point to 1.5, 7.625, all the way till I got to 2.0 and approximately 12.188. So I rounded to 3 decimal places because that's usually what I'm going to ask you to do for any type of problem solving situation. I'm going to ask you to round to 3 decimal places. The reality here is, again, we have a lot of error in this. A step size of 0.5 when we're only moving 2 units is a very, very, very large step size. But when we're working things out by hand, just to get a sense for how this works, that's a reasonable step size to use. If we were really going to solve something like this, if I were going to do this on a calculator using math software, I would have a much, much smaller step size, maybe something like 0.001. And when we get into Euler's method, it's something that you can study at a little bit higher level, start to get into some of these approximation methods. There are ways that we can figure out what size delta x needs to be to get the accuracy that we want out of our solution. So for example, if I wanted my solution to be accurate to 3 decimal places, there's a little calculation that I could do that would tell me, okay, if you want accuracy to 3 decimal places, this is the step size you have to use. And so that's well beyond the scope of this course, but I just want you to understand that we're learning this at kind of a basic level, but this is a really, really powerful tool because we can get really good accuracy with this method by making the step size small. And this is actually a method that you can build more complex approximation methods off of. So for us, that's all you really need to know about Euler's method. You should be able to work out the rest of the problems on that 7.1 assignment using this method. I would ask that you set up a table and actually work it out this way as opposed to writing the equation to the lines, because it's going to streamline your process. It's going to save you a lot of time. But do try in your mind, as you work through these problems, try to envision what's actually happening with those line segments connecting together, like we saw on that geometer sketch pad graph a couple of minutes ago. Okay, so the rest of what is in this packet is just going to be some stuff about using the TI-89. So you really don't need to worry too much about it. I left it in here in case you wanted to investigate it yourself. So this kind of tells you just some basic things you can do on the TI-89. These are some more problems you could try on the TI-89. Again, that's up to you. But what I also put in here is this exploration at the back, which you can use. And this exploration just walks you through Euler's method in a slightly different way. They go through this, obviously it's the same idea, but they set up their table a little bit differently. But what it allows you to do is actually draw in the line segments and kind of see that approximation to the solution curve being created as you fill out that table. Okay, so that's not something you have to do, but if you feel like you want to investigate a little bit further, you're more than welcome to use that exploration to do that. So you should be set for the rest of that 7.1 assignment. And like I said before, I'm going to show you a little bit more about Euler's method during our synchronous time. I'll show you how this works using the TI-89.